Right, so the next lesson is regarding position, velocity, and acceleration graphs and how they relate to each other. So we're going to discuss this in a case-by-case manner, starting with the simplest cases first, and then we'll look at some examples and some comparisons of how you relate the graphs to one another. So first, let's talk about the simplest possible thing an object could be doing. And the simplest thing an object could be doing is actually just sitting in one place, motionless. Right? So this object is at some origin, and it's just staying there, right? It could also be located at some position to the left or right of the origin. Maybe it's at plus 2 meters from the origin, but just staying there, right? And to graph that, we would say, let's graph this one right here. So we would say this thing is at a position of positive 2, and it's just staying there all the time. And the velocity, well, if the object ever moves, then it doesn't have any velocity to start with, and it never has any velocity. And if the velocity never changes, then it has no acceleration. Okay. So notice that the slope of the position graph is 0. And that tells us what the velocity is doing, right? So it's telling us if the slope is constant, this is telling us that the velocity is constant, right? Sorry, if the slope is constant, that's telling us the velocity constant, but the slope is 0, so therefore the velocity is 0. Now notice the slope of the velocity graph is 0, right? And if the slope of the velocity graph is 0, that's telling us what the acceleration is doing, and that means that the acceleration is also 0. So there we go, an object sitting there, not moving. It's got a displacement graph or a position graph that just stays constant straight across, a velocity graph that stays at 0, and an acceleration graph that stays at 0. So the next simplest thing that an object could be doing is moving, right? But if it was moving, the simplest thing it could be doing is moving at a constant velocity. So let's say we have a constant velocity. Let's pick a number. Let's say positive 1 meter per second. What that means is that every second, this thing goes 1 meter in the positive direction. I should have drawn this as a straight line. So 1 meter in the positive direction. Right? So after 1 second, it's gone 1 meter. At 2 seconds, 2 meters. 3 seconds, 3 meters. And 4 and 5 and so on. And 1 meter for each interval of time. Right? And to graph that, we would draw the velocity graph would be the easiest one to draw. That right there would indicate plus 1 meter per second. Now notice that the slope of this graph is 0. Right? The slope is 0. And it's a constant 0, which tells us that the acceleration is also a constant 0. Right? Constant velocity, by definition, means no acceleration. Now, what does the position graph look like? Well, we can graph it out for each interval of time right here. So at 1 second, we've gone 1 meter, and 2 seconds, 2 meters, and 3 seconds, 3 meters, and so on. So we have a constant slope. And you'll also notice that the slope of this graph is plus 1, which is exactly the same as the velocity. So for a constant velocity graph, we have a constant slope on the position graph, a 0 slope on the velocity graph, and a graph of 0 that stays constant for acceleration. Okay, so the next simplest thing something could be doing is moving with a constant acceleration. Now, let's assume for a second that it starts with a velocity of 0. And let's make its initial position 0, just for the sake of simplicity. So, let's say we accelerate at 1 meter per second squared. So we could graph that like this, plus 1 on the acceleration graph, and it's just staying constant, 1 meter per second squared. We have to remember what that means. That means that after 1 second, this object is going to be going at 1 meter per second. And then after 2 seconds is going at 2 meters per second, and at 3 seconds, 3 meters per second, and so on. Now it's picking up speed. That means each second it's going to have a greater average speed for the interval than it did the second before, right? So in 1 second, we go from 0 to 1 meter per second. That's an average speed of 0.5 in 1 second, so we're going to go half a meter. In 2 seconds, between 1 second and 2 seconds, we're going to have a speed, at 2 seconds, sorry, we're going to have a speed of 2 meters per second, right? So at 2 seconds, we got 2 meters per second. At 1 second, we got 1 meter per second. The average of that is 1.5, so we're going to go for 1 second, so we're going to go 1.5 meters, right? And then between 2 and 3 seconds, the average is 2.5 per second, so we're going to go 2.5 meters. So the total is 0.5, then 2, then 4.5, right? So we've got already 2 and then 4.5, so you can see this position graph is curving, right? It's not a constant slope. It's an increasing slope. The speed graph, however, is increasing at a constant rate because at 1 second we got 1 meter per second, 2 we got 2 meters per second, 3 we got 3 meters per second. So we have a constant slope of positive 1, which is, of course, our acceleration. So going forward, if we were to graph these as a block of graphs, right, for something that's not moving, and then moving at a constant velocity, and then a constant acceleration, we can see how this evolves, right? We have constant position, 0 velocity, 0 acceleration. Constantly increasing position, constant velocity, 0 acceleration. Constantly increasing velocity, constant acceleration, a position graph that curves. Okay. Now, what would the next logical step be? Now, this is not part of our curriculum, right? This is not part of the AP curriculum, but we can intuit what the next logical step would be, right? So this is like y equals some constant. Y equals 0, y equals 0. Y equals a constant. Y equals 0. Y equals a constant. And then this is a graph of a constant slope, so it's something like y equals x, or y equals some constant times x. So here we have y equals a constant, y equals x, and then this increases as y equals x squared, right? This is a relationship just between the two axes, right? Not distance and such forth. You know, the x is not the distance, the x is time here. It's the x coordinate, okay? So what would the next logical step be? Well, what if we had a constantly increasing acceleration? So this would be as if this is y equals x. Well, then our velocity graph would increase like our position graph does there. It would be as y equals x squared. And the next logical step here would be, well, it would be the next order polynomial. So y equals x to the third. And you can keep going. You can have accelerations that don't increase at constant rates. You can be increasing at exponential rates, and then the velocity would be y equals x to the third, and the position would be y equals to the fourth, and so on, right? But since this class is limited in scope to situations in which accelerations are constant, we're limited to this set of graphs. Now, this doesn't mean that you're not expected to be able to understand the next level of iteration, right? You should be able to understand it and see why the logic holds. Incidentally, this is a calculus-based approach to understanding this. So let's look at a few examples, right? So let's say we have a velocity graph like this one. Well, what is this telling us? So we're starting out with some initial positive velocity. And what's happening to that velocity? It's approaching zero, right? So this thing is slowing down, right? The speed is decreasing, we're slowing down. And it's happening at a constant rate, which means we have a constant acceleration, right? And the slope of this graph is negative, therefore we have a constant negative acceleration. What about after the zero? Well, look at the line, right? It maintains the same constant slope. So the acceleration for this thing would actually be a constant negative value for the entire interval of time. The fact that it stops and turns around doesn't affect the fact that the acceleration stays exactly the same. But crossing this 0 point here, this is an important inflection point in our position graph because it's telling us that we stopped, right? And when we cross over the axis, we actually turned around and went the other direction, because this is all travel in the positive direction, and this is all travel in the negative direction. But notice that this area is larger than this area. So we're going to have more travel in the positive direction than the negative direction. So let's give it numbers just to help it make sense. So let's say that that's plus 2 meters per second. And so this is 2 seconds. So we have a distance of 2 by 2 for half of that, 2 meters. Okay, so this thing travels 2 meters in the first 2 seconds. So at 2 seconds, we've gone 2 meters. But this graph can't be straight. Why not? Well, it has to curve because we're accelerating. Now, which way does it curve? Does it curve like this, or does it curve like this? Well, here's one way to think of it. In order for the object to reflect that it has stopped, the slope has to be 0. So the slope has to get flatter as you're going towards a speed of 0. So at 2 seconds, we've gone 2 meters, and our slope needs to be flattening out. Now here, if that's plus 2, this is minus 1, so 1 by 1 is 1, half a meter in the negative direction. So this means that we have to, now we're speeding up, right? So our slope is going to be getting larger. The magnitude of our slope is going to be a negative slope, but it's getting larger, so we're going to end here. All right, this is kind of, it's a pretty advanced example, but if you can follow the reasoning, then we're on the right track. Okay. What if our position graph is like this? Okay, so we start with some arbitrary -1 position. And then what is this graph shaped like this telling us? Well, it's telling us that we're moving, right? We're moving towards the origin, and then we go past the origin. Notice that this does not matter in terms of the velocity. If we look at the slope of this segment, the slope is positive, right? It's positive 3, right? 3 over 1, so the slope is plus 3. So the slope of this graph, of this segment of the graph being plus 3, tells us the speed during that segment. So the speed is a constant positive 3. So I'm going to put that here, right? I'm going to label this as plus 3. Our scale is going to be a little bit off for the velocity graph relative to the position graph, but that's okay. So it stays at plus 3 for 1 second, right? Well, then what happens? The graph instantaneously goes to a flat line. What does a flat line mean on a position graph? It means that we have stopped. So this makes our acceleration graph a bit awkward, right? Because our acceleration graph is 0 initially because we're not changing our velocity, but then we immediately, instantaneously change our velocity to 0. So that means that the acceleration graph would theoretically have this big spike in the negative direction would happen really quick and then right back to 0. So sort of a discontinuous point. This would not happen in the real world, right? In the real world, what would happen is at this corner, you really need to have at least some kind of curve, right? But for physics world, right, to keep things simple, we assume that we can instantaneously change our velocities like that. So just so you're aware that this is a bit odd to graph, right, that discontinuity. So you would normally not really see an acceleration graph in this scenario. All right, well, what if our acceleration graph looks like this one? So we have a positive acceleration, then a zero acceleration, and then a negative acceleration. So let's assume that we're starting with an initial velocity of 0. So we have a positive constant acceleration for 1 second. Okay. Now I'm going to call this positive 1 and negative 1. Then we're going to have a constant velocity for 1 second. So our velocity is constant for a second. Then we're going to have a negative 1 velocity for 1 second. So this is going to be a positive slope on the velocity graph and a negative slope on the velocity graph. So a slope of positive 1, 0, and then negative 1. So does this object end up back where it started? Well, if you understand how velocity graphs work, you'll understand that no, that is definitely not the case, because all of this is travel in the positive direction, right? This is travel in the positive delta x direction. So what does it look like? Well, after the first second, we're going to be going at 1 meter per second. I'm going to maintain 1 meter per second for a second, right? So 1, 2, 3. So 1 meter per second for 1 second, and then we're going to stop. So we can actually figure out how far we would have gone for each segment. So the first segment, the average speed is 0.5 for 1 second. So we would have gone 0.5 meter, and this has got to be curved, right? There's got to be a little curve here. Then we're going to go at a constant speed for 1 second at 1 meter per second, so we're going to go 1 meter. Then we're going to slow down, right? We're going to slow down. That means our graph has to level back off. And again, now we're going an average of 0.5 meter per second for 1 second. If you don't understand why it's 0.5, well, we start with a speed of 1 and go to a speed of 0. The average would be 0.5 for 1 second, so 0.5 meters. So we would end up here. So our total distance of travel would be 1 meter. This would be 0.5 meter and 0.5 meter for a total of 2 meters, which is exactly what the scale here would reflect. All right, let's try one more example. So let's say we have a graph that curves like this, and then does that. No, we don't want to do that. Let's say our graph does this, and then that, and then that. Well, we're not going to graph the acceleration here because, again, we're going to have some weird discontinuities. But essentially, so for the first second, what's happening, we're just not moving, right? Then for the next second, we have a negative slope to the graph, which tells us we have a velocity in the negative direction, right? Constant velocity in the negative direction for a second. Then we have a constant velocity in the positive direction for 1 second. So again, we have these weird discontinuities. It's very difficult to graph on our acceleration, so we're not really going to do it. But essentially, what is this saying? Well, this graph says you start here, you stay there, you travel 1 meter in the negative direction, then you travel back to the origin. So the total distance of travel here is 2 meters, but the final position is 0. Well, check this out. We have an area of 1 by 1, so that's a distance of 1 meter, but a position change of -1 meter. We have a distance of 1 by 1, which is +1 meter, and a displacement in the positive direction. The two displacements cancel, and we end up back at the origin. All right, so hopefully this has helped you out a little bit with relating graph shapes to each other, and the basics of the position, velocity, and acceleration graphs and how they relate to one another.